No. There we go. All right. Hey, everybody. Happy Tuesday. Tuesday, right? It is Tuesday. Okay. These weeks go by fast. Sometimes I get confused. Happy Tuesday. It is Tuesday, right? Yeah, it's Tuesday. Good. Okay. So as you will recall, we are in the middle of doing query processing stuff. You have a homework on query processing stuff, and we're about to wrap it up. But there's been some questions that have come up about hashing that I wanted to take a pause and clarify. And then the other thing was there was this poll on Piazza about the course speed, and a good fraction of you said things were going pretty fast. So I thought, okay, let's slow down a little bit. Let's spend a little time, particularly because you're implementing this for your homework. We'll spend a little time just clarifying hashing, and in particular, recursive partitioning, which went by pretty quickly. Okay, so let's review the first pass of out-of-core hashing, external hashing. All right, data streams in from the left. Maybe it's coming from a file scan. Maybe it's coming from a query operator below us. Okay, but data is streaming in. And, we're going to fill I.O. buffer with those rows that come in. So if they're coming off the disk, we'll take a disk block full of tuples and put it right into memory. Okay? And if it's streaming from another operator, we can fill this thing up as we go. But we'll have one buffer in memory, which is the size of a disk block. Remember, a disk block is like 64K. Okay? It's the unit of transfer from our disk. We'll have one buffer for that input flow. The rest of our memory that we've allocated to this task, so assume there's B pages of RAM that we've allocated to hashing. The B minus 1 remaining pages worth of memory that we have are going to be output buffers. And remember, the usual streaming thing. So this thing fills up and then gets transferred via a hash function to one of these. Whenever one of these is full, we write it to the disk, right? And that makes sure that our IOs to the disk are one block at a time big, right? So these output buffers are there to allow us to write these disk partitions and append to them a full block at a time. Right? Every time we go to that disk I/O interface, we want to write a full block. And that's why we need a buffer for each one of the partitions in our hash partitioning. Okay? So we've taken our input stream, we've used the hash function h sub p, and we've partitioned it into these different partitions, right? So h sub p tells us which partition to go to. This is the bad marker. Go away. Bad marker, bad marker. Okay. All right. Now, when we're done streaming these things through and then writing them out sort of one block at a time to these partitions, what have we got? We've got B minus 1 partitions on the disk that capture all the rows that came in. All right, every row that came in is in one of these partitions. And if there are two rows that have the same key, we know they're in the same partition because they hash to the same value. So that's good. So we've divided the problem into subproblems. There's no way that two things that match could be in two different partitions, right? So each partition can now be handled independent of the others. That's why it's a divide piece. And now, in pass 2, we're going to conquer these independently. Good? So in pass 2, here's the thing, is we have B minus 1 of these partitions. We have B pages of RAM. We're going to deal with these one at a time. How big is each one of these partitions, assuming that the input is n pages worth of data? Well, in the ideal case, each one of these is B minus 1 over 2. Sorry. That's it. I don't even know where that came from. In the ideal case, each one of these is n divided by B minus 1, right? We partitioned the n pages into B minus 1 pieces. Okay, but there may be some skew in your hash function or in the duplicates on your hashing key, right? It could be that we're hashing on something where there's a lot of duplicates. So some of these may be bigger than others, all right? But there's multiple reasons that it could occur at the end of pass 1 that one of these things is bigger than B page is big, either because of skew or because maybe this is bigger than B, right? Maybe the input was just really big. So both those could happen. It could happen that just one partition is big because of skew, or it could happen that all the partitions are big because you just had a lot of data. Okay, but it's divide and conquer. So what we're going to do is we're going to treat each one of these independently. The ones that are smaller than B, we go to pass 2. So this first one, let's assume it's less than B pages big. What do we do in pass 2? We read it, less than B pages big, into memory, and we build a big main memory hash table with a finer-grained hash function on the hash key. And that's our hash table that we needed to do the hashing, right? And then if we're doing a group by aggregation, we can aggregate in these hash buckets. If we're doing duplicate elimination, we eliminate duplicates in these hash buckets. If we're doing a join, we simply put the tuples into these hash buckets and then stream another table by later, right? So that's fine if the partition is smaller than B. What happens if the partition is bigger than B? It's not going to fit in a main memory hash table. So what do? We recurse on this whole procedure for this particular, going to be red, partition. All right, so now what we're going to do is we're going to run external hashing on just that partition in red from the beginning, because it's too big. So we start over. So we got this red partition, it's more than B blocks big, and we pretend recursively that we're in pass 1 of partitioning just on this guy. Okay? So it's a one partition operation. So we're going to read in that partition. Let's call it partition P. So we're now going to read in P off of the disk. So actually, why don't we do it in this direction since it was over here. So here's partition P. It is greater than B big. We're going to read it into memory. Right to left this time for no particular reason. Here's our input buffer. Here's our output buffers. There's B minus one of them. There's one. And we use a different hash function. We can't use the one we used up there because it sent everything into this partition. So we use H sub P2, which is a varied hash function. Okay? It's going to split the data up differently this time. And we're going to recursively split this guy into a bunch of little guys. All right? Which are going to be smaller than this guy. Right? And then we're going to, hopefully, those will all be less than B. And we can go to pass 2 on those recursively. Right? And we're done then with this partition. If they're all less than B, we do pass 2 on these guys. We bring these in. Right? We recursively bring these back into a pass 2 hash table. This is pass 1, recursive. This is pass 2, recursive. We do our thing in the hash table, remove duplicates or compute aggregates or whatever, send it to the output, pop out of the recursion, and we are done with this partition. Finished. Okay, we don't ever do pass 2 again on the whole partition because that doesn't mean anything. Okay, so all we did is instead of doing pass 2 on this partition, we recursed and did the whole algorithm on this partition. Right? And when partition by partition, as we go through these, if one of them is bigger than B, we just do that. We just recurse. Okay? Any questions? Yeah.
2 questions. One, first is very basic. The HP is initially the partition, the original data is B minus 1.
Right.
One yourself is not the ultimate.
So let me repeat the question so people can hear it, and we'll see if I understood it. So this first hash function, H sub P, it is modulo B minus 1. So it's going to generate B minus 1 output partitions. Okay? And it's some hash function of our choosing, but it's mod B minus 1. Okay? Did that answer your question?
The second question is for the P, which is bigger than B. Once you return from the recursion, will include all the results. H of P is the same place where it's a lot smaller than B.
Good question. So the question was, what happens to the output inside the recursion of the second phase of P? That is to say, here. This went a little fast. So let me be a little more disciplined here. So this is the recursive pass 1. Let me just erase this. So this is pass 1 recursive. At the end of pass 1, we've got these little subpartitions of partition P. And here's what we're going to do in pass 2 recursive. Let me redraw this. So here's our little subpartitions. Just a copy of this picture. Each one of these hopefully is less than B. If it's not, this whole argument recurses again, but let's say it is. All right. Now this is pass 2 recurse. You read it into memory in a hash table. And then the question is, what do you do with this? So let's say we're doing duplicate elimination. Let's make this concrete. We're doing this hashing because we want to get rid of duplicates. Okay? What we're going to do now is you read one of these guys into memory. All the duplicate values will be together in this subpartition. okay, because they hash together. You remove all the duplicates. You get one value per bucket, and you send it to the output. All right, the same way you would have sent it to the output in the non-recursive case. Plain old pass 2. Also would have gone to the output. All right? So the recursive pass 2 doesn't pop the stack and then do pass 2 again. It just sends things to the output. And when you pop the stack back into not the recursive part, but here there is no pass 2 because this is done. Okay? Another way to say this is out. If you think about the data flow diagrams that we drew, we had scan, file scan, feeding, hash, duplicate elimination, right? When I say out, we're actually returning a next call from the recursion of this partitioning. We're returning tuples from this nested call to pass 2. Returning them back up to whatever this might be main, right? So main says get next. This thing needs to know that it's within the recursion of pass 2 on partition P sub 1. And when it says get next, it'll actually get a tuple out of this hash table. Yes? I would think of it that way. That's right. Yeah, pass 1 partitions the data into these independent tasks, and then pass 2 conquers them by doing duplicate elimination or what have you.
So if there's no duplicates, what's the meaning of pass 2?
If there's no duplicates, then the whole algorithm was a waste of time. So if you knew there was no duplicates, you wouldn't have done this, but you don't know. So you can think of this whole algorithm as the search for duplicates and the assurance that there aren't any. Right? Yeah. Uh-huh.
Are you, in terms of extra time, are you just reading and writing that overflowing partition one extra time each?
Exactly right. So when we recurse, what happens? This partition, P, which is, roughly 1 over B minus, n over B minus, 1 over B minus 1 of the original input n, right? So it's 1 bth, roughly, of n, is going to get written, pass 1 recursive. That thing is going to get written, this way, written. I can't remember which direction I'm going. I'm going this way. It's going to get read, written, and read again. The read was going to happen anyway, because this was pass 2. It's this write and that read that are extra. Yes? Is there a pass 0? Annoyingly, sorting has a pass 0, but hashing has no pass 0. So there is no pass 0 in hashing. It's the way it's been described in the book. So, yes?
Can you explain what your hash table looks like?
Yes. So for the case of duplicate elimination, think of it as a Python dict or a Ruby map or what have you. It's a hash table, okay? And the keys are going to be, so let's give a concrete, let's make this super specific. The query we're running is select distinct last name from students. All right. So as one example here, there may be 2 people with the last name Wu. All right. I admitted 2 people to graduate school this month with the last name Wu, so that's a perfectly real example. This hash table is going to have an entry in it which says Wu, and then it basically doesn't need anything for duplicate elimination. It just needs the word Wu, so that's the key. So it can just say yes. I've seen one of those. And so when I read the second Wu in, I don't do anything here. I just drop it on the floor. At the end, when I'm taking things out of this hash table, I'll take out the name Wu exactly once. Okay? Does that make sense? Now, if we were doing aggregation, if we were counting the Wus, then the first time I saw one, I'd insert it into the hash table with 1. And the next time I saw one, I would increment. So that would be for select count distinct last name from students. Yes. Select count, no. Select count, let's do that one. Select count star from, well, actually, let's do last name, comma, count. Star from students, group by last name. for that algorithm, we would build a hash table with last name as the key and running count as the value. Okay? Uh-huh.
Suppose in your class 1, you will have a partition with duplicates that are bigger than B. They're completely identical items. So that when you're doing the recursion, class 1, how would you have a hash function that splits them into multiple smaller partitions?
Yeah. Great question. So suppose that instead of grouping by last name, we were grouping by gender. This is the classic example, okay? And you have a really big input file, right? So you're going to get a male bucket and a female bucket. And then when you try to recursively partition the male bucket, it'll all land back. It doesn't matter what hash function you pick in one partition again, right? And you repartition, it'll still be one partition. And if you don't have any exception handling, this algorithm will just run forever, recursing and recursing and recursing and making no progress. So at some point, you're supposed to detect that and say, uh-oh, and switch to sorting or something. Okay. It's a very unusual case. Usually the query optimizer will know something about how many distinct values there are in a column and will choose appropriately what algorithm to use. But in the worst case, your implementation of hashing should at least detect this case. I'm unable to subpartition this anymore. And then maybe you call sorting on that partition. Okay? Yeah? Yeah, right. What if the partition is of size B, and in pass 2, actually, we can fit B here. So we're okay if it's B. So we've got all the memory for this hash table. We actually don't. We can use the buffers as we're filling up the hash table to deal with the I/O. And when we get to the end, we can sort of play a little trick and use that last I/O buffer and make it part of the hash table. If it's B plus 1, though, you're out of luck. You have to recurse. Yeah. And that's what the hybrid hashing thing was about trying not to have a step function there. But I don't want to review hybrid hashing because it's not as important. This is quite important. We good? All right. If you're still, working through the details on this, because this is all pictorial, I'd encourage you to try to write it in pseudocode to make sure you understand it, or even write it in Python or perhaps Scala. Right. You're going to end up writing it for your homework. We're not going to make you do recursive partitioning, but you could do that as an exercise to make sure you really understand it. It can be awfully helpful sometimes to write down the pseudocode or the real code. Okay, and feel free to ask your TAs about this stuff. Or come to office hours. Nobody came to my office hours today. It was very lonely. One person came. I saw you somewhere. Okay, anyway. I'm there for you. All right, so that's all we're going to lecture on for query processing. And what we're going to do now is we're going to dive down the stack a little bit. So remember this block diagram, sort of architecture diagram of a database system. And it's a traditional relational database system, so it has a lot of the componentry, some of which you don't need for other systems. And what's missing from this picture is distribution and parallelism, which you can do in a relational database, and we've seen it in our query processing algorithms, but it's not in this picture. So just keep that in mind. If you want to go web scale, you have to think about things like replicas and parallelism. We'll talk about that during the course of the semester also. But in this picture, that's the only thing missing. Everything else that we could think of is probably kind of in here for a traditional DBMS. Okay. And where we've been is kind of in the relational operators. Where we're going now is to the bottom, to the disk subsystem and the buffers above it. And then we're going to connect them up after that with files and access methods so that we'll have done, by the end of, I think, next week, we'll have done everything but query optimization. All right, so we've kind of done query execution and relational operators. We're now doing buffer management and disk space management, and we'll close the sandwich over the course of these 2 weeks. Okay. So a brief note on terminology. This is an irritation. I wanted to make sure it was written down somewhere. The words block and page are being used interchangeably in this class. Some people will tell you blocks are things on disk and pages are things the same size in memory. But the book is not disciplined about that, and neither am I. And so rather than pretend that I'm always going to get that right, I'm just going to say a block is a page is a block. It's a fixed unit of memory. It is the unit of transfer in the I/O interface to the disk. All right? So typically in the book, they'll say that's 4 kilobytes because the book is kind of old. Even when the book came out, it should have been 8 probably. But so the arithmetic in the formulas on the slides and in the book will probably say, assume block size equals 4K. Out in the real world, numbers are more like 64, 128K is a good unit of transfer to set the operating system on for your disk blocks. It's configured typically in your OS, all right, or you can configure it in the database as a multiple of the OS transfer unit. Okay, but we'll assume that it's an abstract number unless we have reason to do arithmetic. Okay, you can't read anything smaller than a block from the disk. All right, so you have to go do a full block I/O to get data off the disk, and that's why we care about it. And then just some terminology stuff. When I say relation and table, those are interchangeable, and that's just tradition. When I say tuple or row or record, those are interchangeable. Again, that's tradition because there have been many kinds of database systems, and they have their different terminologies. And when people say attribute or column or field, I think for our purposes, at least when we're talking about relational databases, those are also synonyms. Okay. And I'll try not to confuse you guys. These aren't hard, but it's annoying, so I'll try to be uniform. I will tend to say, I don't know what I'll tend to say. I'll try to be good. All right, disks and files. So we've talked about this a bit in a previous lecture. Databases do store information on disks. A lot of them are magnetic disks. They are mechanical anachronisms. There's not a lot of devices we use in computing that are mechanical anymore. And this has implications. We have to think about read and write costs, and these are both orders of magnitude more expensive than RAM access. So we've seen this exact slide before, as well as this slide, which is a picture of a disk drive. Recall that these things spin at some physical speed, and there's the cost of moving the disk arms in and out, and then the cost of waiting for the platter to rotate under the disk head. There may be multiple platters stacked up. Transferring from one platter to the other is quick. That's electronics, right? All right, and the page size, this thing that the operating system is forcing us to transfer, is coming initially from some unit of transfer from the physical device. So typically the physical device has something called sectors, and then the page size is a multiple of sectors, and then the operating system might give you a page size that's actually bigger than what the device could do to amortize the cost of I/Os. So there's sort of layers upon layers here, but it's definitely not like memory. You can't access a byte on this thing. You have to get a chunk of data. And from our perspective in this class, just assume it's a block of data or a page of data, same word. And it's always fixed. Okay. The other thing to recall, so seek time, rotational delay, right? Seek time to move the arm, rotational delay to let the data come out, transfer time for the electronics to read out the magnetic media and bring the bits up into your computer. And we saw these numbers, orders of magnitude differences between them. Okay. So we want to try to do things to reduce seek and rotation delays, or simply to not go to the disk drive at all by caching things in memory, or by prefetching things into memory before we need them. Okay. And then lastly, for magnetic disks, sequential I/Os and random I/Os have very different costs because of the cost of seeking and rotational delays. And therefore, we want to think about pages that are near each other on the disk versus pages that are far from each other on the disk. And we can abstract the disk as kind of like an orange that you peel, you know? There's going to be tracks, and we can read them, and then we can sort of concentrically go into the disk drive and think of that as one big spool of linear ordering. And if you actually read the data like that, kind of concentrically or in a spiral from the outside to the inside, it's pretty much sequential I/O the whole way. So you pay very small seek costs and never pay rotational delays. Okay? And in fact, the disk drives with their track buffers and things will make that feel like you're never paying seeks at all. And so there is a notion of sequential scan of the disk, which is way faster than random I/O, where the disk arm is waving back and forth. Okay, so we do have a notion of what's the next block on the disk in some sort of logical linear order. Right? And then when the system knows it's going to do a sequential scan, as I talked about last time, it probably has a thread somewhere that's going to read ahead for you and make that data appear in memory before you even ask for it. Because you'll start reading in order, and the system will go, aha, I see what you're doing, and it'll read ahead for you. Okay, so you can expect that sequential scans are much, much faster than random I/Os. And in fact, they should be as fast as your bandwidth of your machine, right, in a balanced architecture. Okay, so with that background and review, let's talk about how do we actually store data on the disk. Let's get down and dirty. We're going to spend a bit of time on this now. This layer of the system, the disk space manager, this is the lowest layer of the system. It's responsible in most of these implementations for the actual physical layout of bytes on the blocks of the file that the data is stored in. And I think we talked about last time that file, in the ideal case, is actually the device. All right, so in Unix, for example, if you go to /dev/whatever, those are not really files, right? They look like file I/O to you, but they're actually the devices. And you can implement code on top of those to go access blocks on these devices by hand. So for maximum control of performance, you might implement this over the raw device files, right? And then the database system really is managing the blocks of the disk. In practice, that's usually more trouble than it's worth because these device drivers change, and then suddenly you're responsible for every device driver ever written in the database system, and that's annoying. You'd like the file system to give you the abstraction of those devices. So what you do is you allocate a file on an empty drive that's about the size of the drive, and most file systems will be nice and allocate that file sequentially on the physical drive, so that when you say file block 400, file block 401, file block 402, those are physical disk blocks that are actually next to each other sequentially. All right. So we won't talk much about that after this, but just assume that we have management of the space on the disk, and it's pretty much the abstraction of the disk as a sequential scannable disk drive the way you'd expect. All right, so the higher levels of the database system are going to assume that this disk space manager has a very narrow API where it can allocate or deallocate pages from one of these files, and it can read and write pages from these files. And that's kind of all it does. It's a very low-level API. And that if you request a sequence of pages from this API, you'd like that the higher levels would like the sequential access to actually have sequential performance from this lower level. So the lower level is responsible for organizing the blocks of the file to achieve sequentiality when possible. The higher levels don't actually get any guarantees about this, though. So they don't see this. Those physical details of which block is where are behind the API of the storage manager, of the disk space manager. But the higher levels may make some performance assumptions that if they ask for things in sequential order, that the disk space manager will serve them quickly, right? So it's a sort of a performance expectation rather than a physical guarantee between the disk space manager and the higher level. Okay, so the basic abstraction that the database storage manager gives is a file abstraction. So we can ask for pages, but those pages live in files. And the higher levels of the system are going to want to think about records. So we're going to need to map from kind of files to blocks to records in some way in the disk space manager, and we'll see how this is done. So what is a file for database terms? A file is going to be a collection of pages or blocks, each containing a collection of records. All right? And we're going to use the word collection fairly abstractly here, so I didn't necessarily require them to be sequential. How is this different already from the Unix notion of a file? What does Unix say a file abstraction is? Anybody know? It's a stream of bits or bytes, actually. I mean, usually don't think about bits. But yeah, the Unix abstraction is sequential. It's a stream, right, of bytes. So we didn't say anything about streams or orders here. We just said it's a collection, okay? Now, we may expect if we say I want page 2 and then I want page 3, that 3 will come fast. But we won't make any assumptions about actually where they are on the disk or what meaning that ordering has. So these collections are kind of more abstract than in the traditional Unix stream abstraction. Okay? So it's just a collection of pages. Each contains a collection of records. And the API it's going to support is insert a record into this file, delete a record from this file, modify this particular record in the file, fetch this particular record in the file using some record ID. So that's part of this file interface, and I'll show you how we're going to represent record IDs. It's fairly straightforward. And then there's usually an API to like open an iterator on all the records. Right? I want to open an iterator to scan through all the records, get next, get next, get next. All right, and you might be able to pass down some simple kind of where clause conditions on those records into the storage level so that they don't percolate those records up through higher levels of the system. All right, and this is often implemented, by the way, in not just one Unix file or operating system file, but maybe many of them, because a database file may span lots of disks. Right? You may have the table of, say, all clicks that have ever happened on your website, and that could span lots and lots of disks. And the abstraction from the database system's perspective is that's one file, in quotes. Okay? So it's typically implemented as multiple OS files, or you can implement it as multiple raw disk devices. Okay, so the typical file structure is what's called an unordered or heap file. It's a collection of records, and the system guarantees nothing about the order of those records. And as the file shrinks and grows, disk pages are allocated or deallocated to this file. And to support these record-level operations, fetch a record, insert a record, delete a record, modify a record, we're going to need to keep track of what are the pages in the file, where is there free space on these pages so that we can insert records, where are the records on these pages, okay? And there's a bunch of ways you could think about structuring this data on the disk, and we'll go through a few of them, all right? And we'll see which ones we like. And there's trade-offs, as always. All right, we're going to look at two file structures, and then we're going to look at multiple page structures as well. So here's a heap file, right? So no particular order, implemented as two lists, really. So there's going to be some header page, which is where you go when you're interested in this file. It's on a known location in the disk. All right? And then it's going to have two linked lists, doubly linked lists hanging off of it. One of full pages. All right? Well, we won't look at those when we're considering inserting stuff. And one of not full pages, all right, which is places where we might want to insert stuff. Okay? And the location of the header page will be stored somewhere else, like in something called the database catalog, which is where we're going to keep all this stuff. We'll worry about how we represent the database catalog later. It's kind of a bootstrapping problem. But somewhere written down on the side is the location of that header page, and then the pointers let us walk these linked lists of data pages. What's a pointer on the disk? It's an address. What kind of an address? It's not a memory address, because we're on a disk. Yeah? Okay, good. So it could be super physical. It's not, but the one possibility could be it's like the sector of the track of the platter of the device. But the operating system is going to give us an abstraction of just block numbers. All right, so it's just going to be a block number. Each one of these pointers is a block number in a file, in a Unix file. Okay, and that tells us how to go ask the operating system for that block. Okay, so when I draw a pointer here, it's really a disk block ID. Okay. So you can imagine that this has some pros and some cons. And before I give it all away, let's see where we are. Are there any interesting... I don't know if this isn't working. Before we do that, what might be bad about this? It's kind of a straw man, to be honest. It's not a very good organization. What operation might be kind of slow here? Finding a record. Okay. We haven't talked about how you might find a record. Certainly, finding a record by value. Well, suppose we wanted to find all the people named Wu. You'd scan through all the data, but you'd have to do that no matter how you organized it, right? Unless you had some kind of value-based index, and we're not doing that for like 2 more lectures. So regardless of how you organize the blocks, we'll have to scan them all to find all the Wus. Yeah?
It would be hard to see how many free pages you have.
Okay. It would be hard to know how much free space you have. I would agree with that. We might know how long the lists are by maintaining a little metadata at the heads of the lists as we do insertions and deletions. But we might not know how much free space there are in these pages, and more particularly, which pages have how much free space. So if you come along, you're like, I want to insert a record, and it's 2/3 of a page big. Which one of these pages has got that much space? As of now, the only way to do that is to walk through this linked list at the bottom until you find one that's big enough, or that's got enough free space, right?
So why don't we use a hashtag to store the page?
Yeah, why don't we do something better? Yeah, so that's the next slide. So that clearly we want to have some meta information about this. Now you can have that information in memory, which might have been what the suggestion was in front. You could keep a hash table in memory that keeps kind of the state of this disk. And if the system crashes and it comes back up, you could repopulate it kind of in the background or as you go. So that's not bad. We can also organize the disk a little bit better. All right, and we can do both of these things. So you can always keep sort of cached information about the files in memory also. But we can do a better job organizing this thing just a little hierarchically, all right? So instead of having one header page and a linked list, why don't we have sort of a linked list of pointers, a linked list of a sort of directory here, all right? And so this is a fairly typical thing. You store up at the front of the file a bunch of header pages linked together. And the header pages are full of little entries that have a pointer to a data page, that is a block ID, and a free space count. Okay, and you keep them on the disk so you don't have to cache this in memory and recompute it if you crash. You actually put it in these disk pages. And, these directory entries let you know what pages have how much data. So the worst case scenario, you scan the whole directory. You don't scan the whole table, right? And you figure these directory entries are just a few bytes each. So you can store lots of directory entries on a single disk page. So the directory should be pretty small. Okay, so that's one simpler scheme you could do, or a simple scheme you could do that would be much more efficient than one we just saw. right? And I think if you want to do more than this, you start building hierarchies of stuff. Okay, so you might build a directory of directories and organize the pages into collections of things that have more or less free space. But it's usually too much trouble. This is usually enough depth of hierarchy for a single disk drive. Okay, because you can pack these directory pages pretty big. And remember, you're going to take probably a track full of these pages anyway when you go do an I/O. They're all going to be close to each other. So you can get a lot of these directory entries with one sequential I/O, essentially, the cost of one random I/O. All right, so this is probably good enough for most cases we'll be interested in. All right, but the idea of caching some of this in memory and making it even faster is not a bad one. I like that. Okay? All right, so that's just a simple page directory organization. Now, sneak preview of what we're going to talk about either next time or the time after is there are going to be more interesting file structures for doing things more than scans. Particularly, we're going to build indexes that are going to allow us to fetch records by value. So a heap file allows us to retrieve the records by specifying a record ID or by scanning all records sequentially. So what we haven't done yet is talk about what's a record ID, which I guess I'm going to talk about on the next slide. So I'm going to hold that thought. But heap files will allow us to fetch individual rows by record ID. They'll also let us scan through all the rows in random order or in arbitrary order. But it's nice to be able to fetch records by value. Find all the students named Wu. Find all the students in CS. Find all the students whose GPA is greater than 3.0 and have blue hair. Okay? And indexes are going to be file organizations that will let us do these kind of value-based queries. And we're going to learn about B+ trees, which are the standard index for disk-based databases. We'll learn about that in probably 2 lectures. Okay, so just be aware that we're going to be able to do that. These are alternatives to heap files. So you don't have to store your data in this sequential way. You could also store them in indexes. Okay. Now, so this is actually kind of, let me erase a little bit. We're bouncing a little bit around. So what's going to happen is we looked at how you store blocks in a file, right? If you think about it this way, here's what should we draw? Here's a heap file. And we talked about directories and data pages, right? That's the picture on the previous slide. Now, if we zoom in on this thing, we're going to need to talk about what's the contents of a page look like. So there's going to be a picture in a little while, which is going to be what is the layout of a page. But before we do that, inside a page, there's going to be a whole bunch of rows stored in that page, which are rows of a table. And before we actually look at the structure of a page, let's look at how we lay out an actual row or tuple. All right, so we're zooming in one level deeper to how do we store a row. And then we'll pop back into this layer of how do you store a page. Okay. So here's one way to store a record, a row, a tuple, call it what you will. All right. And this is nice if all of your fields of your table are the same width, so fixed width fields, like integers or floats. Then all you have to do is just sequentially, as a sequence of bytes, copy that tuple into the bytes of the disk page, all right? So you have a base address, that's the start of the tuple. You know the lengths of all the fields, because in your table, they're all going to be the same in this example. So it's always, integers are always going to be, let's say, 4 bytes. Right, so column 1 is type integer, so it's always going to be 4 bytes. Column 2 is type integer, it's going to be 4 bytes. So you can compute the location of each field within that tuple as the base address plus the lengths of the preceding fields. So if you want to get to field number 3, you start at B and you add the length of field 1 and the length of field 2. Right? And if in a relational database, all these tuples are going to be the same format, so they have the same columns with the same types, right? And so all the rows in this table will look like that. You don't have to store the field information with the table. You can store it separately in this system catalog. So we know if this is, let's say, the statistics table, that it has 4 columns of type integer. You just store that on the side. And all this arithmetic can be done for that whole table without carrying around that metadata in the storage. Right? This is quite different from something like an XML format in text, where for every field you put the little tag around it that says, this is field F1, right? End of field F1. Field F2. There's a very compact representation. Right? So it's quite efficient. And when you stream this stuff through memory, it goes right through into the processor caches and into the registers very efficiently. So this is a very nice format, and if you know you're dealing with fixed width data. So you want to do this when you can. It really makes things much faster. Okay. Unfortunately, the world is not all fixed length records with fixed length fields. All right, but this is a good thing to be able to do. When it's not fixed length, there's two sort of standard formats. The first one is not very smart, and the second one is better. So the first one, which is sort of in blue, is you say, well, fields could be variable length, so at the end of the field we'll put a delimiter. This is roughly what comma-separated value files do in ASCII format, right? They say, okay, commas are the delimiter. Oh, except that if you have a field that contains the comma character, we're going to have to do some weird escaping with quotes and all kinds of stuff, which makes CSVs kind of painful and actually slow to process. You end up doing a lot of exceptional logic as you read them, right? So you don't really want to have delimiters with special symbols. All right? They introduce branches into your code, and they're just kind of gross. They also make if $sign was your delimiter and you use $sign in your data a lot, you pay the cost of storing the escape characters for those $signs also. So you can have a storage cost. It's generally kind of a crummy idea. The better idea is that at the front of every row or every tuple, you have an array, fixed width array of offsets where you go find that field in the tuple, right? So there's basically, think of them as pointers, but they're just offsets from the front of the tuple. So they're probably 1 byte worth of information to tell you how far to the right it is for you to go to find that field. Okay, so that's a more flexible and compact representation typically. Yes? F4? Well, you'd have to know before you went and got it. So if you're looking at F1, you know where the beginning of F1 is, and you know the beginning of F2 is. And you keep both of those in mind as you go get F1. For F4, there's probably a missing thing, which is an end of record pointer. So I think you're right. There's a little bit of a bug in the slide. Without an end of record pointer or some higher level thing that tells you where the records are in this file, you can't figure out when F4 is done. In fact, that end of record pointer you're going to see lives here at this level. It's going to tell us where the tuples are and how long they are up in the page directory. So we're going to be able to do this, but somehow, somewhere, you need to know the length of F4 or the length of the whole tuple. Good question. Good question. Suppose that, field number 3 is of type text, and I want to change my name from Joseph Hellerstein to Joseph M. Hellerstein. So F3's got to get bigger in this tuple. I'm kind of going to have to rewrite the back half of this tuple over again. True. All right. We're not going to worry about that too much on a tuple by tuple basis because that's all going to happen in memory anyhow. It's not so bad. We are going to try to make that good on a page level basis, as you'll see in the next slide. So I think you asked that question. Yeah. Somebody asked that question. But yeah, you pay a cost here of if you want to expand things, you have to write things forward. The alternative to that would be have these fields floating in the bytes of the page somewhere, right? Which makes page space reclamation a little annoying. Now you've got pointers all over the middles of your pages with different cells of different tuples. So we're going to keep the tuples contiguous, which will allow them to stream through memory better. We'll pay for expanding tuples, which doesn't happen that often. Okay. Good. You guys are thinking about the right stuff. The other thing to wrap your head around in this picture, these are blocks. They're on the disk. We will be reading them into memory. Once we start looking inside a page, we're in RAM now, right? And what is this thing in RAM? It's an array of bytes that happens to be 64K big. And all this stuff we're doing here is byte arithmetic in RAM, right? So all of these pointers are actually number of byte distances, and the arithmetic we'll do on those pointers is like C arithmetic on memory addresses, right? This thing's been read into some particular location in RAM, and F2 is, let's say, 16 bytes to the right of the head of the tuple. So we'll take the tuple's address plus 16 bytes to get to F2, and that's all in RAM. And if we have to change this tuple, we're changing it in RAM, and then we'll manipulate it in memory, and at some point we'll write it back down to the disk. But we'll write the whole block to the disk. Okay, so remember when we're manipulating tuples on pages, that's actually happening in memory. The only thing that happens on disk is writing entire pages and reading entire pages. Okay, finally, let's... one more point on the second thing. Not terribly important, but a lot of times there are fields where you want to put in a null value, which means I don't know. Okay, it can mean doesn't make sense. It can mean can't be computed. It can mean a whole bunch of things, but it's kind of a don't know character. And in SQL and in many languages, every data type has a null field, a null value. It's a special value different from all other values. It's not the same as empty string for strings. It's different. It's null. Okay, so nulls can be represented here just by having two consecutive pointers point to the same space here. Right? So if F2 and F3 both start in the same place, that means F2 is null. Okay, so it's a uniform sort of representation. There you'd have the two delimiters for the two things, which is also fine, actually. Okay, now let's talk about page formats. So I'm going to not talk about row formats anymore. We're going to talk about how do you do a page full of rows. Okay? And again, this is the unit of transfer. So these pages will get read from the disk into memory. On that page, there'll be some tuples copied into that byte array of 64K. Right? Where are those tuples and how do you find them in that 64K extent of memory after you read it up from the disk? Right? We're going to, in the book, so these are the pictures from the book. I'm going to jump forward to this picture. It is an array of memory. So this is 24 bytes of memory, okay? And in all these pictures in the previous slides, which we're going to go back to in a sec, remember that we're really talking about just an array of memory. It's a linear array. But for whatever reason, he draws it as a rectangle. So you have to imagine these rectangles being kind of wrapping around kind of like that. So the actual bytes of memory go like left to right, left to right, left to right in lines. All right, so it's sort of, he's taken that long skinny thing, he's wrapped it around. All right, so on the left here is a page format for fixed length records. It's pretty straightforward. You store the first record in the first bytes of the block, and the next record contiguously right thereafter, and the next record right thereafter, and the next record right thereafter. And then maybe there's some free space. Very nice. It's all at the end of the array. And then at the last piece of the array, maybe it's 1 byte, maybe it's 2 bytes, is a count. The count tells you how many records are on this page. And knowing the number of records, and then knowing from the catalog how wide your records are, because it's fixed width table, then you can compute where free space starts, and you can compute where each existing tuple is at as an offset from the top of the page. Right? So if all your records are 12 bytes long, you know that there's, let's say there n equals 3. You know in slot 1, that's at byte offset 0. Slot 2 is at byte offset 12. Slot 3 is at byte offset 24. You just go get the tuples that way. Okay? Now, as you delete and add tuples, you have to keep this thing compacted, which is sort of annoying, but it's not that big a deal. All right? The other thing you might do instead of that is to choose not to compact free space as you delete tuples. And so you might have empty slots in this page for tuples. They're still fixed width. There's just some slots are empty. And so you'll need some kind of bitmap at the end to say which ones are empty and which ones are full. And you might like to know how many slots there are on the page, although if it's fixed width, you could probably calculate that number m. But let's assume there's an m there that tells you how many slots there are, and then there's a bitmap, maybe from the end of the file going inwards for which slots are full. Okay? And the free space can just pop tuples in and out as they get deleted and inserted. So the only advantage really to the thing on the right for these fixed width tuples is that the tuple IDs are going to stay the same. All right? So this is time to talk about what's a tuple ID or a record ID. In a database system, typically we can refer to records. The only way you can distinguish two totally identical records is where they came from on the disk, physically. And that's going to be a page ID and a slot number. All right? That's a unique physical identifier for the tuple. It's where it got stored. Now, in this left-hand representation, if you keep compacting things, you keep changing the slot numbers of things. I delete the second thing here, then the third thing here becomes the second thing here. Which means that anybody who remembered that record ID of the third thing, and it just got changed, has to be notified and update their memory, and it's a pain in the butt, right? Because you may have other parts of the database, like indexes, pointing to these tuples. And so it's kind of annoying if you move them around, you have to fix all the pointers, the inbound pointers to these things as you move them around. So there's some motivation to use the thing on the right so that when you allocate a tuple on a page, that is its name, and it will stay its name until you do something radical like reorganize the entire file. Okay? So it's often nice not to have a packed representation, but to have an unpacked representation, because then record IDs remain fixed. Okay? Now, this was still assuming that we had fixed width tuples, which is a strong assumption. When it's true, this is great. very efficient. When it's not true, we have to do something else, and you get what's often called a slotted page format. All right? And this is the most general format for organizing a page. What we're going to do is we're going to have, again, a pointer at the very end of the page, which is going to tell us where the start of a big contiguous swath of free space is. All right? So if we need to insert something, we might want to try to find memory for it at the point where that start of free space on the page is. And then we're going to have, 1 byte further in from the end of the page is going to be a number of slots currently on this page. And then for each slot on the page, we'll have a little directory here of 2 bytes each, 1, 2, 3 to n in this case. All right, n entries, which are going to be pointers, really offsets into the page where I can go find the start of a tuple. And what's not in the picture but is in the book and will be on the next slide, we'll also have the links for each of these slot directories of those tuples, which answers the question that was asked before, how do we not read off the end of the tuple? The lengths of the tuples will be stored in the slot directories. So we're going to have the start and length for all the tuples on the page in the slot directory. All right, so you can think about these pages getting even reorganized over time. You can move the tuples on the page around and compact them together to create more free space. The slots stay the same. So there's a level of indirection between somebody pointing from the outside. Say I want record ID, this page, second slot. All right, second slot is that thing that currently now is at offset 16. But if I reorganize the page and I move it to offset 8, that's fine, because the guy out here still called it this page, second slot. Right? So the slot directory is the unique identifier. The slot directory entry is really the unique identifier. The location of the tuple on the page can move. It's that level of indirection between the slot directory and the location of the tuple. Allows you to reorg these pages, which is kind of nice. Okay? And then, because the tuples may be bigger or smaller, we're going to probably want to do this kind of compaction periodically, right? So it's well suited to variable length tables, where each tuple might be a different length, and when you update it, its length might change. Okay? So details. This is the kind of stuff, though, that here at the bottom of the system, you get this wrong, things go slow, and interfaces break, and so you got to get this stuff right. All right? The level of indirection with the slot directory means that these are also kind of nice for fixed length records. And so slotted page kind of organizations get used also sometimes for fixed length records to enable the slots to stay the same. Questions? Let me clarify. So this is a linearization. This is actually the left to right version of a slotted page. So it's 24 bytes long. I'm assuming that we can store these integers in each byte. If you look at the far right, it says that free space starts at byte 13 from the left. There's 2 tuples on this, the orange tuple and the blue tuple. And our slot directory, which goes right to left, in slot 1, every slot is 2 bytes. It's got a start and a length. So slot 1 is the orange stuff. It says it starts at byte 0 and it's 4 long. Slot 2 says it starts at byte 4 and it's 8 long. Okay, what's the biggest tuple that you can add to this page? Well, you might think it's 1, 2, 3, 4, 5. There's 6 gray boxes that are free. So you might think it's 6, but it's not. It's only 4. Why is it only 4? Because we need 2 bytes to put in a new slot directory entry to this new thing. Right? Slot 3 is going to be the thing we add, and it's going to take 2 bytes to extend the slot directory to the left. And then we'll have 4 bytes left to store the tuple from the left to the right. Yeah? Okay. So actually, it might be a good thing to do in section is to just insert a tuple onto this page and see the after image of what happens when you insert that 4 byte tuple, or 2 byte tuple. Okay? So all the pictures before were kind of a little bit, abstract in the sense that they have these rectangles. This is really what's going on in memory when you read this thing off the disk. Right, it's just an array. Okay, so what have we got? We've got heap files, we've got pages, we've got rows or tuples on pages. And then we need to be able to find our heap files. We need to be able to know what the format of the pages are and the rows. And that's going to be off in the system catalog. So somewhere abstractly outside this picture, let's not say how it's implemented yet, there's the system catalogs, which are these Oracle-like, I don't mean Oracle the company, I mean Oracle like the myth. There's a system catalog out here that's going to tell us how to find stuff that we need to know. In particular, it's going to have for each relation the name of the relation, the file location, meaning where's the header block for that file. Right? Where can I go find the header block for that file to start reading it. So there's a physical ID of where that file is. What's the structure of that file? Because that's going to determine what code I invoke to go read from that file. Is it a heap file? Is it a B+ tree file? What is it? Right? And then for that table, we're going to know all the column names, all the attribute names, and their data types. So we'll be able, for the fixed width ones, to figure out how wide they are. And if they're not fixed width, we'll know that. Okay? And then if there are any indexes that are additional on this table, maybe it's the students table, but we built an index on GPA, so we can do quick lookups on GPAs. And we also built an index on last name, so we can do quick lookups on last name. There may be many of these indexes. We'll keep track of which ones there are, and they'll have names, so we can do things like delete them. And then we'll have maybe some integrity constraints on this table, which are things like, properties we always want to be true, like student ID must be unique. That column can't have any duplicates in it. That would be a typical integrity constraint. We'll talk more about integrity constraints over the course of the semester. Those will all be written down in the system catalogs. For each index, we'll know what kind of an index it is. In this class, we'll probably just study B+ trees, but there are other indexes that people use in the field. And it'll tell you what are the search keys of the index. What can you look up with this index? I can look up on GPA, or I can look up on last name. Okay. And then there are going to be these things called views. A view is a query that you store and pretend it's a table. All right, so you can imagine a query which has like the number of students in each major. Compute the number of students in each major. And then you might pretend that's a table and tell someone else about it. You can't see the individual students at Berkeley, but you can see how many students there are in each major. Here's a table that has that information, but it's really just a view. They don't know that under the covers it's a query. It's going to run a query to get the answers. All right, so views are logical tables, and what we store for those is the view name and its definition, the query that goes with it. And then finally, there's a whole bunch of things about like statistics about these tables. So how many pages do they have? How many distinct values are in each column? What's the distribution of values in the columns? Authorization information. What are the names of users? Which users are allowed to look at what? Configuration stuff about the database. How many buffer pages do you have on your machine? All that kind of stuff. So all these things, both physical and logical descriptions of the database, are stored in these catalogs. And the fun thing is that actually the catalogs are bootstrapped off the database. So the catalogs are just relational tables themselves. And there's a little bootstrapping when you boot up the database that it can figure out how to load the catalog tables. And then internally, a lot of the logic to use the catalogs is the same logic that's used to query the regular tables. So the metadata of the system, the catalogs, the data about the data, is just data. Right? So you got nice uniformity. And as a result, you can look at these catalogs and you can query them yourself. So the book has a made-up catalog table here called AtterCat. So this is the catalog table of attributes. What do you need to know about attributes of tables? Well, what is the name of the attribute? What table is it in? What relation is it in? What is the type of that attribute, and what position is it? Is it the first, the second, the third, or the fourth? So this is the table of all columns in the database, according to the book. All right? And you'll see that it actually talks about itself. So one of the relations in this thing is AtterCat, although it's attribute cat, but that's a bug. So it actually describes its own contents. So it says, there is a table called AtterCat that has 4 columns, atter name, rel name, type, and position. It's describing itself, okay? That's fine. That's made up, but this is what you get in Postgres. Right? There's a thing called PG attribute, and \d gives you the column names of a table in the PSQL interface of Postgres. So these are the columns in a real database that tell you about attributes in the database. And there is a relation ID at rel ID, so that's the ID of the relation that this attribute belongs to. There's a name, right? And then there's a whole bunch of other stuff that, in the textbook they didn't think about. I don't even know what a bunch of these mean, but I'll give you one weird example, collation. So if you know anything about internationalization, you'll know that people can decide what the order of things are different than what you might think it is. So the order of strings is something that has been internationally standardized. There's many different orderings you can choose for strings. I think foreign languages might want to alphabetize differently, but it's kind of crazy. So there's a collation field here that tells you which international ordering standard is this column ordered by. When we talk about less than and greater than in this column, what do we mean? All right, so there's all sorts of crazy stuff you need to store. So this is the attribute table in Postgres, and you can poke around. Maybe I can poke around for just a sec in Postgres, and there's a whole bunch of catalog tables. You can do this in your VM. So There's a table called PG tables, I think. It gives you the names of all the tables. And inside the PG tables, there's table names, including PG statistic, PG type, PG auth ID, PG attribute, which is the one we just saw, PG prog. There's a whole bunch of crazy stuff. This is just the catalog of the database. The table names in PG tables right now are just the catalog tables because I haven't defined any other tables. And it goes on, and it goes on, and it goes on. So this is the catalog. It's 58 tables in Postgres. Right? And once you say select star from PG tables, now you know the names of all the tables. You can say select star from SQL languages or whatever. Okay? So there's a whole bunch of stuff in the catalog. You can write queries that join the catalogs to the data if you want to. I'm not sure why you'd want to do that, but there's all sorts of tricks you can play because the catalogs are just tables. All right, so let's take a break, a mental break. Talk a little bit about administrivia. Take a stretch. That's good. All right, homework 1 should be done. It's been graded, and the glookup insertion is going to happen shortly, I think. Michelle's going to get that done today, tomorrow. Something like that. So you should get your grades back on that soon. Homework 1 you had all the tests for, so you know how you did, presumably. Very fussy homework, right? Kind of gross. Kind of gritty, all right? One of the reasons I do that homework, and this is the second time I've tried it, it's an experiment, so it'd be interesting to get your feedback, is that it's a very typical task that you have to do in the real world. Like most times when you get a data set, you have to do junk like this. And most of the tools out there to work on stuff are about as good as the tools you used. So actually a fairly typical task that I gave you. Not a lot of fun, but on the other hand, like sometimes getting down and dirty is the way you really learn to live, right? So we'll be building all kinds of abstractions in this class, right? Relations and tables and query languages and high-level designs for databases, but a lot of times what you get is a bunch of ASCII, and you got to wrangle it. So I did want to give you that feeling, and I'm sorry if it was unpleasant. I hope that you felt like it was worthwhile. But it was a little one. It shouldn't have been too much work. All right, homework 2 is going to be substantially more interesting and substantially more difficult, I would think. And so you should get started on it. All right, and I think we had the Scala info session last night. I don't know how many people were there exactly, Vikram. Maybe 100-ish, so maybe a third of you guys, which is great. Maybe the other 2/3 you already know Scala, which is even better. But I bet a bunch of you don't yet. So watch it on video. It's going to be posted on YouTube. It's been posted, and it's linked from Piazza. Awesome. So if you want to watch the Scala info session at 2x, you can do it twice as fast as your friends. If you don't have a partner for homework 2, you have to get in touch with the TA prontissimo. All right, you're supposed to have a partner by now. We might be a little bit lenient, but it's time. If you call us the day before it's due and say, you know what, I didn't do the partner thing, that's bad. Okay, that could hurt you. Similar comment on understanding Git and turning things in properly. So Michelle very graciously went and fished around for those of you who didn't correctly operate the submission instructions and use Git properly and graded your homework. But on homework 2, we will not be so lenient. So if you can't follow the Git instructions for doing turn-ins, you will lose points next time. Okay? So please pay attention and leave time for the fussy details at the end. So if you did get wrong this time, you didn't hear about it yet. I believe we're going to try to get an autograder going for homework 2 so that when you do your Git push, it should run some tests for you and give you some feedback. That hasn't been deployed yet, so watch Piazza for that. All right, but you will get a note, hopefully, if you used Git wrong on homework 1, and there's some feedback there, which you should pay close attention to. All right, and then the last comment, which I guess is worth saying every year, but if you know the answer to something on the homework, you probably shouldn't post it to Piazza because that spoils everyone else's fun. So just be, if you have a question where you feel like, I don't know if I can ask this question because it reveals a bunch of the answer, use your judgment. I think most of you guys will get it right. If you're uncertain, you can always make the post private. Okay, and if it's something that we feel like it shouldn't be private, everybody should benefit from the answer to the question, we'll make sure that everybody knows. So use a little bit of discretion, common sense, we should be fine. But definitely don't sort of give the answers to things on Piazza full bore, right? That spoils other people's learning opportunity. Okay? Any other questions? Cool. All right. So we finished disk-based management. You know enough to be dangerous. We'll talk about indexes and files that are not just heap files soon, but not yet. First, I want to talk about buffer management. Okay. So this is the interface between the disk management layer and the query operators. The query operators are going to talk about things like next, which is just going to scan. It's going to have a scan over a file. And they're going to talk about things like fetch me this record ID, page ID, slot ID. Those are both things that, in theory, go directly down to the disk-based management system. But we're going to want to do some caching and prefetching into RAM so that those things go faster, right? So between the file access methods, relational operators, all that good stuff we've learned about for query processing and the disk space manager, we're going to insert a caching layer called the buffer management layer. All right? And it's going to do what you'd expect. It's going to do caching. But it's going to be a little sensitive, and as we talk about recovering database from database crashes, it can be very sensitive to the needs of a database system. So it's going to be a little different than the cache manager in a file system. All right, here's an abstract picture of a buffer manager. So below the blue line is the disk drive, okay? So this is the file manager interface down here on the disk drive. On that disk, which we are calling DB, it has pages. One of those pages might be A, okay? Which is some page offset, some page ID. In memory, we're going to have a bunch of disk page-sized chunks of memory allocated for our use as a buffer pool, separate from the memory we use for our query processing operators, all right? This stuff is allocated for a single query, for a single iterator of a single query. It's allocated in RAM. This thing is going to be shared by all queries, and it's going to be allocated when you boot the system. When you boot the database, we're going to allocate some memory for the buffer pool, independent of all those queries. It's going to be shared, okay? And it's going to be however many pages big we configure it to be. But we're going to think of it as being framed, broken into frames, each of which is a page big. And we're going to do replacement in this thing one page at a time. Okay? So the buffer pool is broken into these frames, okay, which are page-sized arrays of memory. And then we're going to, when we read a disk page off the disk, it's going to go into the buffer pool first. All right? We're going to always have it in the buffer pool, because after all, we can't access any of the bytes of this page until it's in RAM. You can't access the bytes of the page while they're on the page. You can only access them once you've read them somewhere into RAM. And that somewhere will be the buffer pool. Okay? All right, so page A might currently be cached in the buffer pool, along with a page X and a page C. They're not necessarily in any particular order in memory in this buffer pool. So we're going to be replacing these pages and putting them into frames completely independently. All right? So data has to be in RAM for the DBMS to operate on it. The buffer manager is going to hide this fact. So the upper layers are just going to assume that they can talk about disk pages. But there's going to be a little lookup table on the side of this buffer pool that's going to say disk page A is currently in frame 1 of the buffer pool. And when you access disk page A, it'll actually point you into memory at frame 1. Okay? So it's just a cache. Pretty simple. There may be free frames. The little lookup table will know which frames are free and which frames are containing particular disk pages. Oh, and then the frames will sometimes have to be replaced, as you would expect, right? If the buffer pool is full and you ask for page Y is not currently in the buffer pool, we're going to have to evict something from the buffer pool so that we can bring Y into the buffer pool, right? And we'll talk about what you do during eviction, but you can imagine that if the page has been changed, you have to write it back to the database. And if the page hasn't been changed, you can just ignore it and throw it away, essentially. So, but we're going to have to choose which page is the best one to replace based on some replacement policy. So we'll talk about these replacement policies as well. Questions at this high level? How many of you took CS162? A lot of you. How much of this sounds like exactly like what you learned about caching in CS162? Good. So what I want you folks to do is look for the differences, all right? And raise your hand and ask questions. You're like, wait, did you just say that? Because that's not what I learned. And for those of you who haven't seen this before, obviously, this is good for you to see. But there's subtle differences between probably what you learned in 162 and what you did here. I will try to call them out, but you should definitely raise your hand for points of clarification. All right, when a page is requested, what happens? So the higher level code, which might be a B-tree package or it might be a file scan iterator, all right, is going to request a particular page. The buffer pool is going to have this lookup table on the side that's going to associate frame numbers, which are the offsets in this memory array that is the buffer pool. It's going to associate those frame numbers with disk page IDs, right? So as we saw, sorry. So Just so you know, my mom is watching these classes now that they're on video. Hi, Mom. And she told me she hopes that I'm actually washing these clothes because they're the same every lecture. Yes, Mom. So it's clean. But it's really hard to see a black microphone on a black shirt, which is what made me think of that. Okay. My mom was a database programmer, so this is genetic. If you have any COBOL questions, I can't answer them, but she can. Okay. This is what I was trying to do. Remember, page A, frame 0, right? Page X, frame 2. Yes? So that's what this little buffer pool information table contains. A frame number, page ID association. Currently, what page is in what frame? We're going to have a field called a pin count, which is going to be how many people or how many tasks have pinned this page in memory, right? And then we're going to have a dirty bit, which is going to say, has this page been changed since it was read? And that's going to be the contents of this side table of information about the buffer pool. So let's see how this works. If you request a page, you being a higher level of the system, and that page is not currently in the buffer pool, we have to find a frame to put it in. Maybe if we're lucky, some frames are empty, but in steady state, they won't be. Okay, so we're going to have to pick a frame that we want to replace. Right, so maybe it's frame number 5. And then if that frame, we're going to look it up in this little lookup table at the top. If that frame is marked as dirty, whatever's there right now has to be written back down to the disk. Right, so all the changes that were made in RAM to that page are now reflected on the disk drive. All right, write that page to the disk, and then read the requested page into that frame. I skipped the thing in blue, though. So the thing in blue says you can't replace a page that's pinned. You can only replace the pages that are unpinned, where unpinned equals pin count equals 0. There's nobody asking to pin this page. All right, so the only things we'll ever replace are things that are unpinned. There better be some things that are unpinned at any given time. All right, if you have all of the pages in your buffer pool pinned, your database system has a bug. Okay, that should never happen. All right, it's called a buffer leak. Right? There should always be free pages. The code that's in the database that's making these pin requests has to make them very short-term pin requests. These are not going to be long-term pin requests. They're going to be pinned and then quickly unpinned. All right. But you can only replace unpinned pages. Now, if the I/O system can predict what pages you might access in the future, it can prefetch them and populate the buffer pool with it. So those requests for pages could come from queries, but they could also come from side processes that are predicting what the queries want and are fetching things in advance of the queries. Okay? So prefetching can happen, and it happens through the same API of requesting pages. It's just happening from another thread. Okay. A little bit more. The requester of a page must eventually unpin it and indicate when they unpin it whether they dirtied it. So the reason you pin a page is because you're about to scribble on that memory, and you don't want it to replace that page while you're changing it. Okay? And then when you're done scribbling on it, you set it to dirty and you unpin it. Right? Now, many people may want to pin this, many people being threads or queries, okay, may want to pin the same page. Maybe they're reading it and they're in the middle of doing some query processing operation and they can't lose it. So there's a pin count. So every thread that wants to work with this page will bump the pin count until it's done and then decrement the pin count when it is done. So pinning a page is pin count plus plus, and a page is a candidate for replacement if and only if pin count equals 0. That's what unpinned means. Okay, so we can have many pins on a page. Now, the concurrency control and recovery units, which remember we're off to the side of that block diagram of the whole database system, you remember? There's the storage layer was at the bottom and so on. Off on the right-hand side was concurrency control and recovery. Recovery is the thing that helps your database when it crashes. Concurrency control is the thing that keeps these different queries from messing with each other. Well, these guys may do some additional stuff when you replace a page. Right? We'll talk about that in excruciating detail later in the semester. All the things that happen to a page before you write it to the database. Don't worry about that for now. Okay? But there will be very typically more stuff happens before replacement than just writing that page to the disk. Log records are generated in particular, and they have to be flushed to the disk. Talk about all that later. All right, but this little bullet at the bottom of the slide is one of the key reasons why the operating system doesn't do the right thing. I need to do some special database magic before my write request is finished. Okay, so you can't just write things when I say to write them. You have to wait for me to do some special, careful tidying around. And then when I do say to write something, well, by God, you better write it. Okay, and the operating system often lies about that. So that's not okay. We need our writes to really be writes. Okay. Buffer replacement policy. All right, and this will feel a lot like CS162. So there's going to be frames. We're going to need to choose how to replace them as a prediction of which frames are going to get used in the future. Right? I don't want to replace something if it's about to get used. I'd like to get the advantage of having it in cache. So we have to predict the future. There's like 50 years of heuristics for this, and they've been all studied on a million different workloads. And good old-fashioned least recently used is still pretty good. All right, most of the time, except when it's not. Okay, and so we'll talk about that a little bit. But least recently used is the most common one. You can do most recently used, which is sometimes the right thing to do. We'll also learn the clock replacement policy. How many of you learned clock in 162? Okay, so we'll do clock again. Maybe this description will be slightly different, but it should be the same idea. This policy can have a huge impact on the performance of your system. And the efficacy of these different replacement policies depend entirely on the pattern of accesses to the disk. Because we're running these big queries, I mean, think about these algorithms, like hashing. There's some very specific I/O behavior in the scans, right, that we know about because we know we're going to do a hash of this entire table. So we know some very sort of large-scale facts about the I/Os we're going to do in the future in a database system that in an operating system you might not know. Right? We have very stylized I/O patterns, particularly in these queries that access tables in the large, the queries that do like big table scans, so analytics workloads. And so the access patterns in a database system can be kind of particular, and we want to tune for them. All right, let's talk about LRU in the context of this buffer manager, and then we'll call it a day. So here's how it works. We want to replace the least recently used frame. The page that is in the frame that was least recently used is the one we evict. That's the frame we get. So if the frame is pinned, it is in use. So it's not recently used, it's currently used. So it's not allowed. We do not replace pinned pages. So ignore the pinned frames. When something is unpinned, that means it's done being used. And that's when we timestamp it. So when pin count goes to 0, that's when we set the use time. That was the last time of use. And then we just look at the frame which has the earliest unpinned time. That's the least recently used in our notion of use. Okay? So pinning and use are very coupled here. It's not just access. It's actually unpinning to 0 that counts as end of use. Okay? It's a very common policy. It's intuitive. It's simple. What's the intuition? The intuition is if you haven't asked for it in a while, then you probably don't care anymore, right? It's just okay intuition, I guess. It works well for sort of hot-cold workloads. So if you have a skewed distribution of popularity, the popular pages will get accessed pretty often. So they'll stay hot, so they'll stay in memory. The infrequently used pages will get loaded in infrequently, and then they won't get used for a while, and they'll get paged out, and that's okay because they're infrequently used. Okay, so it makes sense for these kind of skewed distributions of popularity. Right? It's kind of a hot or not policy. It works pretty well. But it doesn't work well for databases in a lot of cases. Okay, and the usual problem is something that's called sequential flooding. So imagine that you have a file, and you're going to scan it over and over. All right, and we'll stop with this idea, and then next time we'll go through a detail. But here's a file on the disk. It's like 1,000 pages long, and I'm going to scan it, and I'm going to scan it, and I'm going to scan it over and over and over. And suppose you have 100. So this is your file, and this is your buffer manager. And in the buffer manager, you have 100 frames. So your homework for next time is to think about how often you get lucky with LRU in your buffer manager, and you get a hit. Okay, we'll come back to this next time. Get started on your homework.